Hello, everyone, and welcome to the May NASA Night Sky Network member webinar. We're hosting tonight's webinar as usual from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to welcome our guest speaker. Everyone, and welcome to the May NASA Night Sky Network member webinar. We're hosting tonight's webinar as usual from the Astronomical Society of the Pacific in San Francisco, California. An echo. We're very excited to welcome our guest speaker. Everyone, and welcome to the May NASA Night Sky Network member webinar. We're hosting tonight's webinar as usual from the Astronomical. Yeah, what was that?
I think we entered parallel universes.
Did we? It's either that or else, I've got a time turner here that we just
do it again. No, don't do it again.
No, I'm not going to do it again. So they already heard it twice, or at least I did. So
Thanks, y'all.
Okay, so where were we? Well, anyway, we're very excited to welcome our guest speaker, Dr. Eric Mamajek from NASA's Jet Propulsion Lab. But before we introduce Eric, I'm not sure whether it's Vivian or Kat at this moment, so it's somebody with some announcements.
I'll take this one. Welcome, everybody. If this is your first webinar with us, we invite you to join us for many of these. We have them almost every month. You can find the link on YouTube. We'll put that in the chat, or you might already be there. We have a couple of upcoming things for Night Sky Network members in particular. There's a cosmic conversation. So after each of these, if you are a member of your local astronomy club, you can join us again next week, a week from today, May 22nd at 5 p.m. Pacific, 8 p.m. Eastern. For cosmic conversations, we'll follow up and talk about some of the ways that we can integrate what we hear tonight into our public engagement. So we hope to see you there. I think, are you able to put some chats? Oh, she's got it. Thank you so much, Kat, for putting that in the chat. Let's see what else. Oh, on May 21st, the day before, we have a Color Your Universe workshop, and this is referencing the library summer reading program. So if you've done it's an activity from the Big Astronomy Toolkit all about how we use filters in astronomy. It's a great activity, and you're welcome to join us for that. That's open to absolutely everybody. If you know your local librarian would like to join, it's a free workshop that the Astronomical Society of the Pacific is putting on. That's where we're joining you from tonight. And then for amateur astronomers in the Night Sky Network, we are so excited to share with you a brand new solar toolkit, and that's going to come to all of the active clubs in the Night Sky Network. That we're going to be mailing that out, I believe, beginning on Monday. It could take us a few days to get it out, but keep an eye out for it in the next week or two. I'd say in the next 2 weeks to go to your club's mailing address. If you are not sure if your club is active, we'll put a link in the chat to make sure you can find your club and make sure you're active. Thank you. Kat is on top of it. Great. And I believe that's all for me. Oh, no, so the Solar Toolkit, we're going to have a little meeting to talk about it, and we can all get together, and it's not a webinar, it's more of a chat about all the new things that are coming in that. And that's June 3rd. I'm sure you put that in the chat. I just can't see it. Thank you. And we look forward to seeing many of you at many of those places. I'll hand it back to you, Brian.
All right, thanks. So as always, remember, we've got the Zoom chat that you can use that. Please make sure that you select everyone and not just host and panelists. It looks like, Eric, you actually ended up with sending a note to host and panelists, not everyone. So even we do that. There's also the Q&A window. If you have any questions for Eric this evening, please put those in the Q&A window, type those in those. That really helps us to be able to keep track of the questions. And if you have any technical difficulties, please put that into the chat, or you can send us an email at nightskyinfo@astrosociety.org. So again, let's welcome to the May NASA Night Sky Network webinar. Dr. Eric Mamajek is a principal scientist at NASA's Jet Propulsion Laboratory in Pasadena, California. Since 2016, he has served as the Deputy Program Chief Scientist for the NASA Exoplanet Exploration Program, managed by JPL4, the Astrophysics Division of the NASA Science Mission Directorate. He grew up on a horse farm in Pennsylvania, earned his BS in astronomy and astrophysics at Penn State, a Master of Science from the University of New South Wales, and his MS and PhD in astronomy from University of Arizona. He's worked at all kinds of different observatories and all kinds of different NASA missions. And without further ado, let's welcome Dr. Eric Mamajek.
Hello, I'm going to share my slides here. And there we go. Okay, I'm assuming you can see my slides.
Yep, they look great.
Okay. Thank you so much for having me. This is my first time at the Night Sky Network webinar series, and I'm very pleased to be able to give a talk here. And Chenille, thank you for part of the invitation too. I've known Chenille for about 20 years. So, so let's just get started here. Talking a little bit about exoplanets and the quest for discovering Earth-like planets around nearby stars with the Habitable Worlds Observatory. And I'll sort of go from exoplanets to HWO to some discussion about the target stars. I suspect many people here remember this. This was Voyager 1 in 1990. I was in high school at the time. This was the famous family portrait of the solar system and the image of the Earth from a few billion kilometers away. This is the famous pale blue dot suspended in a sunbeam that Carl Sagan described. And this was a very inspiring image around 1990, and I think it made a lot of people think about what planets would look like if you were imaging them around other stars. I mean, this was using a small telescope on a spacecraft a few billion miles away. This was Voyager 1. The reason it's looking down on the solar system was it went on a trajectory. It did Jupiter. It launched in 1977, shortly after I was born. Went to Jupiter, did a flyby of Jupiter in 79, and in 81 it went to Saturn. And this one they committed to go close to Titan. And in doing a very close flyby of Titan, its trajectory took it way up out of the ecliptic. So Voyager was sort of looking down on the solar system. And this was a really interesting image, and it was right at the dawn of the discovery of exoplanets, which really started in the 1990s. There's some interesting tales of and work that went on trying to discover exoplanets during the 1980s, but the early 90s is when the field really started to take off. Anyway, so this was the famous pale blue dot, and I was one of the people looking at that thinking, wow, what would it look like, detecting Earths around other stars? When this was taken, I think the first confirmed exoplanets had just been found. I don't think announced yet, actually. It was probably within a year. They were planets around a pulsar discovered by Alexander Volshin and Doug Frail using radio astronomy. So another interesting paper that came out afterwards, and around 1990 is when the Galileo probe was launched to Jupiter. And the Galileo mission, if you remember that one had the probe that went into the atmosphere of Jupiter to save on fuel. It took a very interesting trajectory, a Vega trajectory, VEEGA. So it went Venus, Earth, Earth. I can't remember what the G was. Was it Gaspra? Did fly by, I think, one or two asteroids. But it passed Earth twice. It got gravitational slingshots out of the inner solar system to go to Jupiter. And Carl Sagan led a paper here in 1993 that was looking at it was analyzing the Galileo data from the flyby as if Earth was a planet we weren't familiar with, like a totally different way of looking at the Earth. And looking for signs of life. What was was there anything in the data that Galileo could measure in the spectral imaging? And the things that stood out Well, they saw strong absorption features here between 0.7 microns and 1 micron, which was indicative of water and oxygen. That's a very interesting sign. And as you went further into the infrared, you can see the x-axis there, the wavelengths. This is all, well, 0.7 to 1 is very, 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 very near infrared. And you see sort of 2 to 3 and 4 to 5 micron images on the right. And you start to pick up other gases, water and carbon dioxide, nitrous oxide. And one of the things that was noticeable was methane was out of equilibrium with oxygen, which is very suspicious. You need some source of the methane. The oxygen itself is very interesting. How'd you get such an oxygen-rich atmosphere? And so, this was an interesting experiment just to think about, well, what would exoplanets look like from a distance, and how would we interpret their spectra? Nowadays, scientists are thinking of a lot of different quote unquote biosignatures, and the biosignatures are really just not the gases themselves, but combinations of the gases that would give you a signal that would be indicative that you probably have a source that's biogenic. However, one of the interesting things that's popped up with biosignatures is scientists keep coming up with new ways to create combinations of the gases um, that may not require biogenic source. And so, for example, if you have a water-rich planet orbiting an M dwarf, red dwarf star, that's subject to a lot of irradiation close to its star, and you break down the water, you can produce a very oxygen-rich atmosphere. And so there's people have been finding sort of niche cases, and so this has been an active field of study. What combinations of gases should we be looking for that would indicate life? And so you can see on the left panel is Earth. We see oxygen, ozone. You don't think of ozone that we need it. Well, we need it for keeping the ultraviolet rays at bay from burning us, with limited success here in Southern California. But ozone is a very sensitive indicator of oxygen. Even if you have very, very weak oxygen, can barely detect it, you can have a booming ozone feature. You kind of need the oxygen to produce that ozone through photochemistry in the upper atmosphere. And water, of course. We've got our greenhouse gas, carbon dioxide, and what our photosynthesizing plants love. And methane, again, is sort of out of whack. You don't expect to find an oxygen-rich atmosphere with a lot of methane. Anyway, so these are combinations of gases that astrobiologists have been thinking about over the years, and thinking about what cases in which they may be very suggestive of life. Now, the Earth that we think of now, we just see a snapshot of the Earth. I mean, we are actually seeing the Earth subtly changing in time over our lifetimes, because we are contributing gases to the atmosphere. So things like, carbon dioxide, methane, nitrous oxide. These are some of the gases that have been increasing in recent decades, and started to uptick in the last century or two. So we're actually somewhat changing the composition of the atmosphere. If you look in the lower left corner, this is what a reflection spectrum of the Earth would look like if you divide through by the sun. As you go to the left, you can see that rainbow there. That's the visible part of the spectrum, about 0.4 to 0.7 microns from purple to red. And as you go left, you get into the ultraviolet, you see that big whopping absorption feature, O3. That's the ozone. That's protecting you from the sun. And as you go redward, you start to see some small features there. There is some ozone features in the red. There's some O2 absorption lines. So you can detect the oxygen we breathe. You can see water absorption. And as you go out towards 2 microns, you can also pick up, there's some subtle carbon monoxide and methane features. But that's just a snapshot of what the Earth looks like now. The Earth has been multiple planets over its lifetime. It has changed as life has evolved on the planet. If you go back to Proterozoic Earth, earlier than about 0.5 billion years ago, the ozone feature was probably more subtle. There was lower oxygen, perhaps about 1% oxygen in the atmosphere. So you can imagine if you were looking at the Earth over hundreds of billions of years, it probably had a less oxygen absorption, less ozone absorption. And about 2 billion years ago was the so-called Great Oxidation event. So the Earth's atmosphere went from negligible oxygen to increasing oxygen, now about 20% oxygen. So this has had a big effect. This is a byproduct of life itself. Um, and as you go really far back, go back to Archean Earth, probably about the first billion years or so in Earth's history, it could have been very different. Oxygen may have been basically non-existent. You may see things like methane much more pronounced, water more pronounced. We could have had hazes as the sun was more active. There was more ultraviolet and X-ray photons hitting the Earth's atmosphere, doing more photochemistry in the Earth's atmosphere. So instead of a nice big absorption feature, we could have had a haze of small particles instead. We could have been a pale orange dot. People have been using geological constraints and looking at the, trying to estimate what the composition of the atmosphere was going back in time. You can see how big the uncertainties are in that plot on the left. But the spectral features probably would have subtly changed. Now, as we look out to other stars, we're going to be seeing stars at a whole range of ages. We can see planets at different points in their evolution, with or without life. And so we may see a whole zoo of absorption features. If you look on the right, those are some example cases. Those are actually hypothetical planet spectra with some, there's Venus there in the upper left. But like the next one down is if you moved a Neptune to 1 astronomical unit, what would it look like? And those large planets, you start to see very strong absorption features from methane. And so we can model both, constrained by our observations of the planets in our solar system, but running the computer simulations and from constraints on our chemistry and what we know of opacities and molecular reactions, we can make predictions of what the planets may look like. But as we look out to other planetary systems, we're probably going to see a whole zoo of spectra and very different examples of things than we see in our solar system. So as I mentioned, around the 1990 was around the first planets were discovered. The first radial velocity planets were reported in 1995, the first ones that really held up, so-called 51 Pegasi, the hot Jupiter. We're reaching the 30-year anniversary of that, and the field really took off after that. Radial velocity, if you remember, that is so-called Doppler spectroscopy. If you take a spectrum of the star, take the star, spread out its light, look at the chemical absorption features, there are techniques for measuring the radial velocity of those features very precisely. And the breakthrough in the 1990s was getting down to the few meters per second level of precision. And so once you get down to a few meters per second, you can start picking up very large planets, and especially large planets close into their star. So in the 1990s, early 2000s, we saw a lot of hot Jupiters discovered, a lot of very close-in large planets. Well, since the early 90s, the number of exoplanets discovered, first off, the number of techniques proliferated. Besides radial velocity, we have transit. If a planet passes in front of its star periodically, we see dips in the light. We can detect transits. There are ones that have been discovered through direct imaging. That's very challenging, but there's a few dozen that have been imaged, usually giant planets at large separations. There's so-called microlensing. So planet either orbiting its star or all on its lonesome floating in the galaxy can pass in front of a star and actually produce a gravitational microlensing event predicted by Einstein in the 1930s. We can actually detect these. And so there's several techniques now. And the number of planets basically doubled till about 5 or 10 years ago, doubled about every little more than 2 years. It's tailed off a little bit since 2016, but the number of candidates is going to pick up again. That trend of doubling about every 2 years is going to continue as we get candidates from a few of the upcoming missions. TESS has produced about 7,000 candidates, and as you see here in the middle, about 627 of the TESS planets are confirmed through other techniques. It's been about 25 or so, about 100 per year, about 25 per quarter. We have to track them. So there's been a steady pipeline of planets from the TESS mission, which is looking for these transiting planets. I'll talk about the Kepler mission here soon. Kepler found a couple thousand planets. And there's a few upcoming missions that'll find a lot more. So those numbers, especially the number of candidates, is probably going to take off to tens of thousands, perhaps over 100,000 by 2030 or early 2030s. So we're getting a deluge of these planets. They range in how well we can characterize them. Some of them are becoming very well characterized. We can detect them through multiple methods. The James Webb Space Telescope, now folks are able to probe the atmospheres of some of the close-in planets in the infrared. So the field has really taken off. I was an undergrad at Penn State. My first research summer was 1995, 30 years ago. Exoplanets barely existed as a field. You would go to meetings, there might be 2 or 3 people, might be 1 or 2 talks on exoplanets. How times have changed. I went to the Winter American Astronomical Society meeting in DC in January. There were times where there were 5 or 6 sessions going on simultaneously, all talking about exoplanets. And this went on for days. So the field has really taken off. In some of the upcoming discussions here, I'll be talking about the habitable zone, potentially habitable planets. I just wanted to put us on the same page here. What is the habitable zone? People sometimes misunderstand this. I love this quote from my friend Stephen Kane. He's a professor at UC Riverside. It says the entire purpose of the habitable zone is as a target selection tool so that limited resources may be used more effectively if the purpose is to optimize observations for biosignature detection. In other words, if you're looking for small rocky planets similar to Earth with atmospheres not too different from Earth, although you can enhance the greenhouse effect and some of them move the planets further out. You can change how much water is in the atmosphere. If you make the planet not too exotic off of the various axes of what makes the Earth, that is it. You can use that as a search tool, but it's not limiting that life may not be, we're not saying life may not be found outside of the habitable zone. But if you want to go look for Earth-like planets and you want to detect them, you want to image them, you want to take spectra of them, this is the way to go. Okay, so in our system, you go a bit inward of the Earth, it gets too hot. You could boil off the oceans, produce a runaway greenhouse. As you go too far away, the Earth would freeze over. You'd increase the albedo, make it too shiny. You decrease the temperature. You'd glaciate the whole planet. Looks like the Earth has kind of gone through that a couple times. So-called snowball Earth episodes. You can keep adding greenhouse gases. You'll say, I'll make up for that. I'm just going to keep adding CO2 to the atmosphere. Yeah, you can do that until the carbon dioxide gets so cold, it freezes out in the atmosphere and turns to clouds, and it becomes shiny. So there's an outer limit on how far you could put an Earth-sized planet, and it's close to the orbit of Mars. If Mars was much larger, it might be marginal as a habitable planet. But this is not precluding the existence of life, for example, on icy ocean worlds in the outer parts of systems. It's just those moons are very small compared to the planets, and they're very, 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 very difficult to detect. So as tough as it is to find an Earth-like planet around another star, it's factors of 10 even more difficult to find moons around giant planets. So these habitable zones, basically we're looking at the areas where the amount of light that you get from the sun, from the star, is similar to what we get from Earth. They scale roughly as the square root of the luminosity of the star. And in fact, in that upper, you see the solar system in the bottom there. In the top is the TRAPPIST-1 system, famous transiting planet system. I believe it's 7 or 8, 7 planets. Orbiting a very, very tiny star, and they're orbiting very, very close in. That system's almost more like Jupiter than it is our solar system. But it has a little habitable zone, and 3 of the planets are within the habitable zone. But they're probably very different planets. They're probably tidally locked to the star. They've probably been exposed to a lot more ultraviolet radiation and stellar winds. So they may be having, they may be tidally locked. They may be undergone very different evolution. So really what we'd love to do is go look for planets around sun-like stars that are not subject to some of the same extremes that these red dwarf stars are producing. To further motivate things here, this is an image from Cerro Tololo, one of my favorite places to observe on Earth. I used to work there about a dozen years ago. You can go out there sometimes. It is so dark. There's no lights. You can just see the stars and occasionally some bright planets. And you actually see your shadow on the ground or on a against a dome, that shadow is from the light of the galaxy, not the sun or the moon on these really dark nights. It's absolutely incredible. So you look out, you see all these stars. We see thousands of stars with the naked eye. The galaxy's got billions of stars. And you wonder, well, how many planets are out there also? And we've just started the survey looking for planets in the last few decades. Probably the deepest search was with the Kepler mission of NASA's. And they basically pointed at one region of the sky and looked for planets that transit and found a few thousand just in one region of the sky in Cygnus. So here was the famous Kepler spacecraft launched in 2009. Mission ended in 2018. It had a very long extended mission that observed some other parts of the sky. That's a whole other story. Now you can take the results from Kepler and sort of extrapolate. Well, what did Kepler find exactly? Well, if you look at our galaxy, sorry, I'm getting background objects here. There's something like 40 to 80 billion solar masses of stars in our galaxy. And if you look at the local stellar populations, your typical star weighs about 40% the mass of the sun. Your typical star is just a run-of-the-mill red dwarf. If you divide those numbers, you get a number something like about 150 billion stars in the galaxy. Okay. Now, what Kepler did, Kepler looked at the statistic, detected a couple thousand stars out of hundreds of thousands of stars, but it was only detecting the ones that were edge on that happened to pass in front of their star. So you can take the Kepler results and sort of extrapolate, what about the planets that I missed? And if you look at those statistics, you basically find that planets are ubiquitous. Okay, far more common than nearly every star you see probably has planet or planets. M dwarfs, the red dwarf stars, probably have more than about 4 planets per star. And that result is just for things less than a 256-day period, less than a year. So the red dwarfs tend to have very compact systems of multiple planets. The sun-like stars, for periods less than about a year, have something like a planet and a half on average. And that's just down to about half the size of the Earth, roughly Mars size. Okay. So we've got 3 planets for periods less than 400 days. Okay. This is just for close in orbits. This is not even extrapolating beyond. And there's a whole bunch of discovery space out for periods beyond a year. But the overall result, if you digest the Kepler results, are planets are ubiquitous. Star Trek was right. Everywhere you go, there's a planet. So the minimum number of planets you get from the statistics from Kepler, if you extrapolate over the whole galaxy, you get something like more than 500 billion planets in the Milky Way. That's a minimum. That's just counting up the ones close to their star. So we're probably talking trillions of planets. Now, if you start thinking about the habitable zone and say, okay, I'm going to look just for planets similar in size to the Earth, and maybe down to a little bit smaller than the Earth, a little bit bigger than the Earth, over the radii where I could take an Earth and change its parameters a little bit, but still make it habitable, still meaning liquid water on the surface for an atmosphere typical for a rocky world. If you take those statistics from Kepler, those look like, on average, there's something like a quarter of an Earth-sized planet in the habitable zone per star in the galaxy. The red dwarfs, it's probably about 1 in 3. For the sun-like stars, this is varied. It's somewhere between about 0.1 and 0.6. The recent astronomy decadal survey adopted 0.25. Something like 1 out of 4 of the nearby sun-like stars probably has an Earth-sized planet. Could be a little bit bigger, could be a little bit smaller, could be a little bit further out, could be a little bit closer in, but in that parameter space that's kind of close to what we see for Earth. So if you extrapolate over the whole galaxy for those, then you get something like 50 billion-ish temperate rocky planets in the Milky Way. Wow. Okay. And just to put an exclamation mark on that, the nearest star, Proxima Centauri, at 4 light years away, we now know has an Earth-sized planet in its habitable zone. The nearest star to us beyond the sun has a HAB zone planet, Proxima Centauri b. So that's a pretty good sign, right? You've seen one dandelion, there's dandelions everywhere. Okay. So planets are common. Earth-like planets are probably pretty common. Let's go find them. This is a nice graphic, just came out earlier this year from the Carl Sagan Institute. If you go through and add up the smaller planets that are in there's various definitions of the habitable zone, but let's adopt this is I believe, the optimistic habitable zone. Um, this is the distribution of how much light the planets receive versus the temperature of the stars. You're going from hotter stars like the sun at the top to dim red dwarfs at the bottom. And then you see all those planets there of varying size, and you see the Earth at the top. One of the things you notice, we have found the community has found of order 40-ish planets similar in size of the Earth and orbiting the habitable zones of their stars. And as you see, the vast majority of them are around stars much cooler than the sun. Most of them are around red dwarfs. It has been very challenging to find ones around Earth-like stars. There's a couple Kepler objects there. The closest one's Kepler 452b. Some of those are a little bit controversial. They were very small signals in the Kepler data. There's people working trying to follow them up and reanalyze the data. This was detecting a couple thousand planets, and it was only a few here. There was just some breadcrumbs of planets that ended up being somewhat similar to the Earth. But statistically, the astronomers have been extrapolating over these results and estimating how many might be filling this parameter space. Multiple techniques have been finding these planets. Many of them were found through transits. A lot of the ones, the dim red dwarfs, have been found through the radial velocity method from the ground. So there's multiple techniques to find these planets, but you can see the ones like Earth are rare. So now this is looking at sort of progression of NASA missions through the lens of these National Academies decadal surveys that come out. Since 1972, about every decade, the National Academies gets a group of astronomers together and they write a report basically spelling out what the big science challenges are and what they see as mission concepts that could go after those scientific mysteries. And the big one from 1972 was Hubble, which launched, I think, about 17 years later. That was just, this is the days before adaptive optics. It was like, put a 2-meter class telescope in space, you will make a ton of discoveries. And Hubble is still running, has been an absolute discovery machine. The Chandra X-ray Observatory was proposed in 1982. It's been functioning for a quarter of a century. It was launched in the around 2000. The Spitzer Space Telescope was proposed in 1991. Actually, it had a bit of a life before that. That one ran a very successful infrared mission in the early 21st century. The James Webb Space Telescope, which we're starting to see discoveries from, just launched a few years ago, that was the top recommendation of the 2001 decadal survey. And so these have been telling Congress, telling the taxpayers, telling the community, the community has provided white papers of input to the National Academies, and the panel has produced this report. Here's all the cool science that is really advancing the field, and here's some types of space-based and ground-based projects that can really go after that science. The 2010 decadal had the Roman Space Telescope. It's a very interesting observatory. It's going to launch here soon, I think in 2027. It's going to do it's basically Hubble with a very wide field imager on it. And so you can do large extragalactic surveys and test for dark energy and dark matter through multiple methods. They're going to image the galactic center, the galactic bulge, and look for microlensing planets, and also pick up tens of thousands of transiting planets in the meantime, looking at the very dense center of our galaxy. Roman is also going to be, as I'll show later, that is going to test coronagraph technologies, which are going to be very important for the Habitable Worlds Observatory. It's going to look for faint things next to very bright things and test those techniques. The most recent decadal that just came out in 2021 proposed a new large space telescope, much bigger than Hubble, similar in size to the James Webb Space Telescope. But the James Webb Space Telescope was operating mostly in the infrared, as you've seen the images from it. And so the resolution is not as good and that needed for finding Earths. And you want higher contrast imaging. You want to be able to detect very faint things next to very bright things. And so you need more advanced so-called coronagraphs for blocking out the starlight. And so this is in the lower right corner here. This is just sort of a hypothetical scene of a sun-like star. If you put the sun at 12 parsecs, about 40 light years away, this is what it would look like if you had a hypothetical space telescope. This was for the LUVOIR concept. This was one of the pre-astronomy decadal concepts for a large space telescope. But you need to get down to very low planet star brightness ratios to detect down to 10 to the minus 10, 1 part in 10 billion to detect Earths. So the decadals had a big recommendation. It said after a successful mission technology maturation program, NASA should embark on a program to realize a mission to search for biosignatures from a robust number of about 25 habitable zone planets and to be a transformative facility for general astrophysics. And coincidentally, it'll do great for observations of solar system bodies as well. And so it advocates if the mission and the technology maturation is successful this decade, that it should go on to a launch sometime in the first half of the 2040s. As you see from the ARCA missions here, these large missions do take time. There's technologies to advance. There are instruments to design. These are very complicated. These are not just, putting a very simple instrument on a rocket. These are really tailored instruments optimized to do these scientific observations. So since then, that concept has been dubbed the Habitable Worlds Observatory. And it has sort of, people have started, there's a lot of interest in it in the community. So the scientists are sort of, sharpening their pencils and trying to work on the formulation of this mission. There's now a project office at Goddard. There's a science office here also at, and some technology development here at JPL. And these are some of the science questions here that they envision habitable worlds going after, not just looking for Earth-like planets around nearby stars, which is sort of a big challenge. But there's a lot of other cool science in cosmology, planetary science, astrophysics, things that go bump and explode in the sky, interstellar medium, galaxy formation, black holes, you name it. So this is basically going to be a super Hubble, probably a 6-meter or larger version of Hubble, but and with a whole suite of imagers and spectrometers, but able to detect to do high contrast observations and to detect Earth-like planets around nearby stars. That is really the big technological challenge. This is a cool plot I came up with a couple years ago. I've been slowly editing over time. This is how I'm sort of seeing the search for life among NASA and astrobiology. And I have these tiers here, okay, these arrows. That top yellow arrow, this is one path, and I call this exo-Earths orbiting sun-like stars. This is if you use a large space telescope, you directly image the Earths, and you try to separate out their light and study them. Okay, that's one way to go. The Roman Space Telescope is on there. That's going to advance the techniques. The Habitable Worlds Observatory we're looking at as a long-term goal. If you go much larger than that, you have to start thinking about interferometry because you just can't build the telescopes that big. And so you may need networks of multiple telescopes. So that's a far future concept, something that might be thought about for the upcoming decadals. That red arrow, the second one down, we call this the red dwarf star opportunity. This is trying to study Earth-like planets around red dwarf stars using transit techniques, or from the ground, you can do from spectroscopy and high contrast imaging. The red dwarfs are a different kind of challenge, okay? So this path, we've got the TESS mission discovering a lot of red dwarf candidates. The James Webb Space Telescope is now conducting observations, transmission spectroscopy and transit spectroscopy, probing the atmospheres of these planets. It has been very challenging. The stars are variable. The planets are extremely weak signals, and so we're sort of in the early days of doing observations with James Webb Space Telescope, trying to figure out what they're telling us about small rocky planets close into M dwarfs. But that path, the red dwarfs also offer opportunity for large ground-based telescopes, perhaps to try to detect oxygen if you can commit large amounts of time with these large ground-based telescopes. And you may want to think about an infrared telescope in the future that may be able to do more transit studies. And so that's one path. The bottom two, another way to look is in the solar system, right? Go look for solar in situ signs of biological signatures. Mars sample return. We've got a rover on Mars right now that is drilling these interesting samples. They need to come home. Bring them home. We need a robot to go to Mars, or somebody to go to Mars and go pick these up. Um, there's Mars is one destination. There's also the icy satellites in the outer solar system. Dragonfly is going to go to Titan and helicopter run on Titan, study probably prebiotic chemistry. There's a concept called the Enceladus Orbitlander. So there's places in the solar system we can go look for life. In the bottom, I have this thin blue line. This is the wild card, which is technosignatures, right? Earth is the solar system's 4.5 billion years old. About half the stars will be observing are older than the solar system, upwards of 10 billion years for some of them. Some of these systems have had a lot more time for life to evolve. Could there be advanced life out there? The stuff of science fiction. And there are some opportunities. There may be ways of studying, and people have been thinking even how to detect things like gases from pollution, from even using things like Habitable Worlds Observatory. And obviously people are looking in the radio, things like the Green Bank telescope, the Sphere-X at launch. You may be able to look for heat signatures from very large structures. There's some interesting ideas. Technosignatures may be a bit of a cheat card in the search for life. So I like to think of these arrows. If you had $1 in pennies, where would you put your pennies? Okay, most of my pennies are on the yellow one. My job is counting on it. Looking for Earth-like planets around sun-like stars. It's probably going to take a while, but I think that's probably the best route to go. But we don't know. We may be surprised by detecting life even in our own solar system. There could be a technosignature detection, radio detection at some point. Red dwarfs are a tough way to go. It's good people are studying them, but it's a very tough environment. Okay, I'm gonna have to speed things up a little bit here. I wanted to show this plot. The x-axis is angular separation between a star and a planet. And we're down in arc seconds. Okay, so the typical blurring you see in the Earth's atmosphere is around 1 arc second or few arc seconds. So now we're trying to look down to separations that are much smaller than that. If you were to with a space telescope, the y-axis is the brightness ratio, the light between the planet and the star, and you can see these are really, really tiny numbers. We're going from 1 part in 1,000 to 10 to the minus, 1 part in 10 billion, and even lower than that. So these are very, very tiny amounts of light, and we need to make sure the star is not blurring or covering up that light. So this is kind of complicated. As you go to the upper right, that's where we're at now. Those curves in the upper right, there's James Webb Space Telescope, there's Hubble Space Telescope. Those are the contrast limits. The star-planet brightness ratio is a function of separation in the modern era, and they're mostly giant planets. Those planets that are listed there are mostly giant planets at wide separation. They're fantastic. We're learning about large planets, but and that's actually thermal light. That's the intrinsic heat from those planets, which is another different ballgame. If you see in the bottom left corner, you see Earth. Okay, so the curves on here are if you put the Earth at 10 parsecs, 33 light years away. Typical sun-like star, 10 parsecs. So you see the Earth would be at 0.1 arc second separation and 10 to the minus 10, 1 part in 10 billion. That is really challenging. So most of these stars would be able to study with the Habitable Worlds Observatory. They're within 10 or 20 parsecs. They're down in that regime around where the Earth is plotted there. And you can see we're several factors of 10 from here to here, okay? The Roman Space Telescope is going to be a big advance in terms of testing chronograph technologies. It's going to get us down, we think, to the 10 to the minus 9-ish level, but not quite down to the Earth's. It may be able to see some large planets around nearby stars, may get down to the Neptune or sub-Neptune regime, but probably mostly giant planets. But it's still going to be a major advance. Okay, so that's a big instrument on Roman. It's going to be launched in 2027. If you look on the left side there's Proxima Centauri. Some of these very tiny stars, red dwarfs, you can get much larger planet-to-star brightness ratios because the planets are much closer to the star. But they are very, very difficult to study. You need a very, very large telescope, and it's easier to build an extremely large telescope on the ground than it is in space. So the future extremely large telescopes like the European ALT, TM 30-meter telescope, Giant Magellan telescope, there are some planets that they'll be able to go after among nearby red dwarfs. So you can see the challenge here. This has been people have known we need to get to this level of 10 to the minus 10 for a long time. It's there's a lot of people are trying different chronographs, doing a lot of testing. It has been difficult. So thinking about habitability, right? On the left here, this is from the one of the concept studies before the decadal on a large space telescope. We try to think, if you're trying to come up with the full picture on the habitability of a planet, you've got to ask all these different questions. There's different levels of observations that you can do. And basically step one is you need a target list. You need to go after the systems where we think there are Earths. Even before you launch the spacecraft. And that's kind of where we're at now. But you can see there's different levels of information. You eventually want to know things like you want to search for water, and then you want to know about the star's activity level. You want to measure their masses. You want to search for the biosignature gases. You want to have as complete a picture as you can in interpreting those, if you measure the spectrum of an Earth-like star. And so this is just quotes. I'm not going to read it this is quotes out of the Decadal Survey, but basically it's arguing we really need to know the stars well, and to be able to put the spectra of the stars, spectra of the planets in context. This is a cool cartoon from a review by Vicky Meadows and Rory Barnes. This is factors affecting potentially habitable worlds. There's a lot of complicating effects here, right? What are the things that sort of make the Earth Earth-like, and affects things that will affect other worlds? There's a slew of effects that from the star itself, right? The brightness of the star, the age of the star, the winds from the star, the magnetic field of the star, variability of the star. That star probably has planets. You've got other planets in the neighborhood. Jupiter's probably had a big impact on the Earth, both in terms of controlling the migration of materials that ended up accreting into the Earth early on, and later in carving up the asteroid belt and delivering asteroids with volatiles later. And then there's the planet itself, right? It's like how big is the planet? What is it made of? Does it have a magnetic field? Is there an atmosphere? Is there an atmosphere capable of shielding UV? Do we see hazes? What's it? There's all sorts of questions you can ask about that. And some of these things are observable and some are not. Some, if you've got a big enough telescope and a big instrument, a well-designed instrument, you can detect them. Some of them you're probably going to have to infer the properties from some other parameter. So there's a lot of factors that'll go into whether a planet is habitable. Case in point, the Earth is in the so-called habitable zone of the sun. Well, the moon is in the habitable zone of the sun. Well, the moon is obviously not habitable. The moon's very small, doesn't have an atmosphere. There's a lot of factors that can preclude a planet from being potentially habitable. And so, if you detect the light from it, you'd want to know as much about it as you can. How are we doing for time? You probably need to finish up here soon.
Yeah, if you could get done here in the next few minutes, that'd be great.
Okay. I just want to say there's been a lot of excitement about thinking about the design of the Habitable Worlds Observatory. We've had a few meetings here over the last year and a half. This is very interesting. It's almost thinking about the early days of, when they were designing Hubble back in the 70s. We're at the very early stages of thinking about what instruments we want, how the instruments should be designed. How would you do surveys with those instruments? And so, the scientists all have a lot of different things they want to work on. Search for Earth-like planets is just one of those. And so here's a mix of the community working groups, many different topics here. People thinking about galaxies and stellar evolution, and there's people working on the technology. There's people doing simulations of the science. There's a lot of action going on here. I'm part of one of the groups called the Living Worlds Working Group that has been thinking about how Worlds Observatory would do a search for Earth-like planets, and I'm co-chairing the group on the target stars and systems with my partner in crime here, Natalie Henkel from Louisiana State. this is, I'm just showing you one page of this. There have been a whole bunch of hypothetical science cases for the Habitable Worlds Observatory. People were using their imaginations and thinking, what sort of observations would they like to do? How, what requirements would the telescope need? This is one page just in the, on some of the planet science cases. There's many of these. There's been dozens of science cases submitted that will factor into designing the observatory. So I'm just going to breeze through this here. I'm co-chairing this Habitable Worlds Target Star group. We've been thinking about what target stars the Habitable Worlds Observatory would observe. They tend to be mostly the nearest sun-like stars. And we need to think about, what do we need to know about these stars and when do we need to know it? There's some things we need to know now for doing the simulations, the yields of the science and detecting biosignatures and things like that. And then there's things we can measure over the next decade or two to improve our knowledge of those systems. So this task group is shout out to these folks. They're the heads of the task groups on all these different aspects of these nearby stars, the stellar properties, multiplicity, high energy emission, activity and rotation. And we have experts on all these different aspects of what we know about stars. We're also thinking about what is known about the planetary systems and what do we need to know about planetary systems about those stars before Habitable Worlds Observatory would launch. The distribution of the target stars at this point, this is just a snapshot of where we're at. That plot on the right, this is distance versus luminosity of the star. Those are in logarithmic units there. So 1 is a factor of 10, 2 is a factor of 100. So basically big stars at the top, big luminous stars at the top, dim stars at the bottom. And you have this interesting pi wedge of stars, and they mostly tend to be 0 would be the sun on here, a luminosity of 10 to the 0. And you see most of them are within 10 or 20 parsecs of the solar system. Why does it look like that? Well, why does it have that weird distribution? The ones at the bottom, you're running up against being too close to the resolution limit of the telescope. And that's limited by the wavelength of the telescope, the diameter of the telescope, lambda over d for the astronomers and the optics folks. That defines the bottom. On the right side, the planets just become too faint. There's just not enough photons coming from those planets. And at the top, you run into another interesting constraint. Those planets are those stars are so luminous, the habitable zones are far out. And so the planet has a finite size. It's actually reflecting less light, and it's harder to disentangle that light from the star. So that produces a constraint. So you can kind of explain why it has that distribution of shapes. But your typical target is something like a sun-like star at about 10 or 12 parsecs. And there's all sorts of other effects we need to know about stellar binaries. Probably about half of these stars are in binaries. Do they have planets in the habitable zone already? If there's a big Jupiter sitting there, it probably doesn't have an Earth in the habitable zone. Dust disks are going to be a problem. We're finding dust around some stars, and they present a background that makes it more difficult to observe. I just wanted to advertise this feature on the NASA Exoplanet Exploration Program website on target stars. I'll just leave the HTML up there for a brief time. But the best targets we found so far, there's roughly a list of about 164 of these provisional targets, sort of the best of the best systems. You can go, we have some information on these. You can go visit the star. You can fly around in the so-called eyes on exoplanets and go between extrasolar planetary systems. I think I'm going to pass on this. This is just thinking about requirements of what we would need for the radial velocity techniques and the astrometry techniques to detect Earth twins around these nearby stars. And it is tough. We've got to improve radial velocity from the right side here. We need to be able to measure better velocities, and we need to move down. We need to be able to measure astrometry, measure the positions of the stars much more accurately. We need to get down to the sub-micro arc second regime for astrometry. We need to get down to the sub-10 centimeter per second regime for radial velocities to measure the masses of these planets. That is a big, big technical challenge. And we kind of need both techniques. No single technique can do it, measuring the masses of these planets. Okay. So anyway, so this is just a list of some of the precursor science cases that the working group has come up with. What sort of information do we need to inform the design of the observatory and how the surveys would be done? And so I'm just going to take us back to that pale blue dot in 1990. And I'm hoping sometime here in not too distant future, we start seeing images like this of pale dots around other stars. This is a hypothetical planetary system at about 10 10 parsecs. And that pale blue dot will be something like 29th or 30th magnitude for the astronomers. And we want to measure spectra. We want to see the chemical signatures of the atmospheres of those planets and look for combinations of those chemicals that might hint at life. So I just want to put my acknowledgments up and thank you. I'll take any questions.
All right. Thank you so much, Eric. This is really great. And I'm really glad that you left that you came back to the Voyager image, because we had a question early on about the camera sensor and resolution on Voyager and kind of the comparison between that and the sensors that you're going to be using.
The detectors on Voyager, the imagers on Voyager, I don't know what they were. They're from they must have been state of the art probably a few years before the 1977 launch. So I actually don't know. I don't know what sort of detectors they had. I don't know if that was reticons. They certainly were. This was pre-CCD era, pre-CCD and very much pre-CMOS. So I think they have a much smaller dynamic range. I don't know how many. I don't think they're able to digitize them as well. If you look at the Voyager data.
Well, it just kind of points out the I guess the serendipitousness and the achievement that they had to come up with those images of the pale blue dot. So it's so we have a good question here. Do scientists have an opinion about photosynthesis being as rare as intelligent life itself? I know you had that chart there showing how I guess the amount of various gases in the atmosphere changed over time.
Yeah.
And so, is this an active thing that people are thinking about photosynthesis as, I mean, it'd be great to be able to detect the signs of photosynthesis, let alone intelligence.
I have one of the world's experts on photosynthesis just down the hall, Nancy Kiang from the KISS Institute in New York City, who's visiting. She's been thinking about photosynthesis for planets orbiting other stars. But for Earth, photosynthesis, there seems to be evidence of life really far back. There's been very controversial evidence, I think back to 3.8 billion years or something like that. And then the evidence sort of gets better until you get to the mid threes and billions of years. I mean, some of the oldest rocks we have on Earth, in Greenland and Western Australia, South Africa are pushing, 3 to 3.5. And there seems to be very, very early evidence of life. So photosynthesis probably started very early, and it must have taken a long time. And that was a waste gas from methanogens originally. Stromatolites. We probably had many huge spans of time where stromatolites were very dominant. Now they're limited to very tiny coves in Australia. They're very rare. But we probably had very different we had oxygen produced as a waste product. It just happens to be fantastic for cells that are expending energy and doing things like building larger animals and muscles and things like that. So it seems like life evolved very quickly. Photosynthesis probably evolved very quickly, and photosynthesis seems to work even in a wide range of conditions on Earth. I mean, there's photosynthesis in very different types of light levels in the oceans. Apparently you can tweak the input light to different parts of the spectrum. People have been trying to break photosynthesis. It's very resilient, and there's multiple paths to do those reactions, and you produce wonderful oxygen that we like. And now it's 20%. If it was much more, we'd be having even more fires than we're already having. But for long periods of time on Earth, oxygen was probably nearly undetectable, and it's gone from about 1% to 20 some percent here in the last um, half billion years.
So I do want to follow up with just, I know we're at the top of the hour, and so I want to get to at least one more question. Related to that, if Europa Clipper discovers some really good evidence of that Europa has the environment for life, will those findings have an influence on what you're doing with these other missions? Will that influence how you're looking and characterizing these exoplanets?
That's a really good question, because Europa is a weird case, right? It's a very small icy moon, negligible atmosphere. It's about the size of the Earth's moon, but it's so close to Jupiter. Like if you're looking at it from parsecs away, it'd be very, very difficult to disentangle a satellite from the light of a giant planet. But the interesting thing you would say is, wow, if life can appear on Europa, it can appear. I mean, if it formed there in such, in um, given the environmental constraints, the radiation, that by being close to Jupiter, lack of an atmosphere, but it has an ocean and there's heating in the ocean, tidal heating. If life could form there, you'd think, I mean, if life can form on any other planet in the solar system, you'd think, oh, wow, it must be easy to form and resilient. The problem is with the form, because if it's in our solar system, um, the Earth rocks kicked off of the Earth in large collisions have probably been polluting the planets in our solar system for billions of years with stuff that was on Earth. We pick up Martian meteorites all the time. We pick up, lunar meteorites. We've got samples of other rocks, from other bodies in the solar system on Earth. Um, there's probably rocks that have been kicked off Earth. There's probably meteorites on Mars that are Earth rocks. Um, so, there's been material delivered from Earth to other bodies in the solar system. So you'd wonder about, was it really a second genesis of life that had started independently, or was it seeded by, panspermia, from the Earth and from the solar system? It's tough to tell. I mean, you look at the chemistry of the life and be able to say, okay, this was a very different type of life. But boy, any signs in the solar system, I'm a huge fan of these solar system missions. Let's go do them. Let's find out as much we can, between Mars, Europa, and Enceladus. Titan is an extraordinarily different environment. We want to know more about the processes that can take place on these bodies. So I hope they do find life in the solar system.
And presumably those processes are taking place in these other solar systems
Yeah.
As well.
Yeah, I mean, one thing we're learning, the sun is an extremely ordinary star. It's a very well-behaved star. We see tons of stars like the sun. Alpha Centauri, the nearest sun-like star to us, Alpha Centauri A, is very similar to our sun, slightly older, similar rotation periods, similar magnetic cycles. And from Kepler and radial velocity surveys, we know that planets are ubiquitous. So this, and chemically, the stars seem to be very similar to each other. There's this range in the compositions, but we see the trends, and planets like the Earth, made of similar stuff as Earth, are probably extremely common. So I think there's no reason to be pessimistic at all for finding evidence of life on biosignatures on other planets. But we'll be looking at these planets. They're all different ages, right? Look at Alpha Centauri. They're a little bit older than the sun. Go look at Epsilon Eridani. It's about 500 million years old. We'd be looking, if it was an Earth-like planet there, we'd be looking in the Archean. If we look at Tau Ceti, it's probably 9 billion years old. It's twice as old. So it's planets, things like plate tectonics might have shut down. It may have had more time for the planets to lose their atmospheres, and the star's luminosity may have turned planets into greenhouses. So we're going to see a whole range of different types of environments and evolutionary histories. We're going to see planets in all different phases in their life, just like we see humans in all phases of their life.
Yeah. All right. Well, I want to apologize for the other questions that we need to end it here, but so I apologize to the questions that we're leaving unanswered. That's all for tonight. Please join us next week for Cosmic Conversations on Wednesday, May 22nd. Actually, that's Thursday, May 22nd. And our next webinar is on Tuesday, July 22 there's a bunch of 22. So hopefully I got those other dates right. When we will welcome Alina Gavrilenko, who will bring us up to date on the Lucy mission to the Trojan asteroid. So thank you very much, Eric, for joining us this evening. And thank you everyone for tuning in. You can find this webinar along with many others on the Night Sky Network YouTube channel. So keep looking up. We'll see you next week and next month and the month after. So take care, everyone.
Thank you.
Oh, this is great. Thank you so much.
So much fun, but you're muted. That was really great. Thank you.
We look forward to seeing what all this is, and I think we'd love to have you back sometime too. So
Oh, hopefully with good news.
Yeah, no
hopefully with
kidding.
good news.
Aliens.